Hi, welcome everyone to this last session on reuse and expand models. Today, we will delve into how this impactful concept applies to the modeling process. The concept of reusing models is widely used in our daily life. Take modular furniture, for instance. It embodies a flexible approach to interior design, allowing adjustments and expansions to meet evolving needs without the need for constant replacements. This cost effective strategy mirrors the principle of modularity seen in other fields. In software engineering, libraries and frameworks are prime examples of reusing and expanding models. Developers often leverage existing code libraries to add functionalities or fix issues without reinventing the wheel. Open source projects are particularly notable for their collaborative nature, where contributions from the global community expand the capabilities of the software over time. Car manufacturers frequently reuse and adapt existing vehicle platforms for new models. This approach allows them to reduce development time and costs. For example, a single chassis design might be expanded or modified to accommodate different types of vehicles such as sedans, SUVs, and electric cars, leveraging the initial investment across multiple product lines. Even in machine learning, rather than building models from scratch, leveraging pre trained models can significantly reduce both computational demands and development time. Today, we will explore this principle hands on through the model of an analog synthesizer. We will see how creating reusable components not only generates new sounds but also speeds up the design process. Let's dive in step by step and uncover the potential of reusable models together. I see that we have Leo with us today.
Right.
Yes, hello.
Right. Right. Yeah. Hi.
Hi, Leo.
So with that, so before we start, uh, like diving into our hands-on example, we said reuse and expand models, right? And I covered some
Right.
examples, very broad examples from everyday life or from industries. But how do we relate that to our modeling approaches, or how does how does this principle help us in our modeling day-to-day life?
Right. Maybe we can remember our one of the examples. Which one was that? Like the voting process, right?
Right.
Over there, we had like a physical votes coming from the ballots, and also we have the postal votes. So instead of creating uh, same type of voting process, what we do, we create a one generic component, which was a base class, a modular in a way. We just take that component and rename it and also change the parameters. In principle, they both the same, but they had different system parameters,
Right.
and we
Right.
could reuse that thing.
Right. And I think the principle is same as when we use components from the business simulation library or components from the Modelica library. Like some
Exactly.
library developer has taken a concept, created a component for you, for us, and then we could reuse it to create our own systems. Like the business simulation library based on the system dynamics metaphor, and we could use it to model various real life systems. And talking about
Exactly.
various real life systems, we have Leo today, who will Leo, what is an analog synthesizer, and what is your take on reusing and expanding models? Like, how do you use it in your day-to-day life, or when you create those analog synthesizers? Can you just be, can you just for our audience just give a brief of what you do and how this principle helps you in your work?
Yeah, specifically in electrical engineering, we work a lot with components, and the probably the easier to understand case is when you buy like an integrated circuit, it has a bunch of components inside, and when you want to simulate it, you don't really need the whole detail of that integrated circuit. And for a complex circuit, what you do is you may use different or multiple instances, and each of those components can be turned into larger components and then reuse it as needed. So in this case, this image that you are showing is some of the work that I do for signal processing, and this is a simulator called VCD Rack. So what it does, it simulates an old school analog synthesizer, and you can see in the image that there are a lot of controls. There are a lot of jacks where you can connect signals, and the idea is that when you want to create like a sound producing machine, you take a bunch of these modules and you connect them together. And similarly, in System Modeler, while I'm developing these modules, I follow a similar approach. I have a bunch of components that I can instantiate and then just use and combine with others in order to create more complex behavior.
Right. And I copied some of your models, and I also shared some of your models with our participants today. And this is one of the model that you had. You had different blocks, and then you created a techno music out of it, right? And and like, what is this circuit, Leo? Like, what are you trying to do here?
Right. So this is the way. This is like a simulation of smaller components, and those small components are a simulation of different electrical circuits that combine together produce a sound. I don't know if we're going to go into the details of this, but I can give you like a small idea on how the
Yes.
sounds are generated.
Yes. I think, Leo, we will go into that. Um, uh, right. Okay. So um, right. So just for okay. Um, sorry, I forgot what I wanted to say. No, okay, let me get back. Okay, so Leo, we have shared the models, the components that you have used in your work with our participants, a small subset of it. And the idea for today was to just start with one very simple circuit. And with the first circuit, we will try to understand what are the different ingredients needed to generate the sound. We will look at a very small workflow which all our participants can actually reproduce, right? And then one circuit we will go in full detail, right? And then we will, and for the other circuit, we will just look at the end result, right? So that's the plan for now, right? Okay, so let's get started, Leo. And as we get into the model, you can perhaps give us more idea of what we are trying to do, right? Does that sound all right?
Yes, yes, that's fine.
Okay, so in order to get started with today's session, let's open System Modeler, and then we will use the modeling principles package. I'm using modeling principles version 2 package, but if you had the old modeling principles library, that will also work, right? So the models are the same. And then we will use the reuse models sub package inside this. We'll go to exercises, and we will start. Let me delete this. I forgot. While preparing for this session, I had those components already pre-made for us, right? Uh, let's look at the solution for exercise 1, and this is the first model that we will try to model using our exercise package, right? So Leo, we have a few components here. We have something called a, we have a pulse signal, which we have called an audio. We have a sawtooth signal, and we have a filter, and then we even have a periodic clock, right? So this is a hello world example using the filter component from your sub library, right? So what are we trying to do here? Like, what is the importance of each component that we are seeing here?
Yes, so what we are doing here is, as we mentioned at the beginning, is it's a sound synthesizer, and it's based on a principle in which uh, the main audio is generate is it's a, how to say it. So these analog synthesizers started when they were started development. They were using oscillators to generate waves, right?
Hmm.
And one of the easiest way to generate is like a pulsing wave, and
Hmm.
that has a lots of harmonics. So it sounds like a, if you remember like Atari sounds, like old school sounds of the video games, it sounds like that. And the idea is that that's a wave, that sound can be shaped a little bit in order to reduce like some of that harmonic content, or shape it in a special way.
Hmm.
And for that we use a filter.
Okay. Right.
So, and the filter is being controlled in order to change the characteristics of the sound.
Right. And if I double click on my filter, I get into the component view where I see that this filter is actually not a mathematical filter, but you have used your actual electric circuit that perhaps you use in your modules, and you want to test your modules before you deploy it, right? Or what is the purpose of this electric
Right.
circuit?
That is a simple RC circuit. And we can see in the top there is the potentiometer,
Hmm.
and it's receiving a signal that is basically it is basically like one of these buttons of the synthesizer, and
Hmm.
it's in we are simulating that we are twisting the knob.
Right. And the voltage input is the pulse input that you mentioned,
Yes.
right?
And
Okay,
we are
so
measuring, yeah, the voltage of the capacitor, and we will get like this filtered signal.
right.
So this
Okay.
is a digital replica of real physical system. You're saying,
Yeah, it's a simulation of what will be an analog circuit.
Right.
yeah.
So Leo, when you create your actual modules, you actually create your own circuit boards, right? And before you create your own circuit boards, you test your models in system modeler, and then you do it.
Right, like part of the design process is simulating the models in order to determine like what are good component values, etc.
Mhm.
And once I have validated those, I can go into the next step, which will be uh, building the actual circuits, and also just
Right.
corroborate that the results are correct. So yes, the simulation it's a very important tool in the
Right.
design process.
So Leo, can you quickly summarize why using this type of simulation tool before doing the all the circuits by hands? So what type of advantage you get?
Yeah, so the possibility of changing values, of changing components. For example, I can build in a breadboard a circuit and place some components, test it, and what usually happens is that I, for some reason I don't like it, or it's not exactly what I was expecting. So I have to take another component from the
Oh,
component bin, replace it, put it, test it. But indeed, if I use simulation, it's just a matter of running multiple simulations in order to get the behavior that I expect, and then I just go straight to the components that I need when I build the circuit. Is very very close.
oh, I see. I see. Yeah, it gets all the process gets way faster than
Yes.
by doing hand. Okay. Yeah.
Right. Okay, so Leo, as you explained, we will start modeling this simple circuit where we have a filter, we have an audio, which is basically the oscillator which represents the oscillator. We are passing it to the filter to remove some certain harmonics, and this sawtooth is basically we are mimicking turning the knob, right? If I'm not wrong. So that's what we're trying
Yes.
to mimic using the sawtooth signal. And then I see that we also have something called we have a periodic clock with a frequency of 44.1 kilohertz. Like, why is this needed when we do this, when we try to get the simulation results?
Right. So basically, what the system modeler is going to try to do, the simulator engine, what it's going to try to do is to find the fastest way of solving the equations, and for that, it will control how fast time progresses. So it can make like long jumps if necessary. It's just based on the amount of error, and if the error is small, it will just perform like longer jumps. But
Right.
with this, but the addition of this periodic clock, what we are doing is forcing the simulator to make a stop every 44.1 kilohertz, which is like uh, a good sampling rate for an audio signal. So
Right.
what if this sample if we have like a lower sampling rate, what happens is that we get like a degradation of the sound,
Yeah,
and
it is based
and
on the
this one,
Nyquist-Shannon sampling theorem, right? Because we can hear
yes,
up to 20 kilohertz of sound, and then to get a good sampling, we should have twice the frequency, uh, and that translates to around 44,000 plus other details which I don't know.
right, yes, and in this case, this sampling frequency is the same that we get in audio CDs.
Okay. Also, Leo, listening to the your explanation on periodic clock, perhaps one could also, without using the clocks, one could actually go for explicit fixed step solvers and try to fix the step size so that it matches it matches the intervals, right? And that could
Right.
also be a way of doing it.
Yes, but it is recommended to use the periodic clock to force the simulator to stop, because these other methods are not as good and accurate as Dazzle or CVOD is.
Okay. 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 Okay, Leo. We had a lot of explanation. Now let's get our hands dirty and let's try to create our model. Okay. So let's open the blank step one canvas. And then uh, first we will use the filter, and that filter component can be found inside the components package. So all these components that are present here, those components have an electric circuit under the hood, and those have been developed by Leo when he tries to create his circuits, right? And for this we will use a simple RC filter. There is a silent key filter as well, but for now let's use this RC filter. uh, Now once we have the filter, we need the pulse and the sawtooth source, and those two can be found in the Modelica blocks component. So we go to Modelica blocks, and here we have the sources. So Modelica blocks sources, and here we have different types of sources. We will use the pulse to mimic the oscillator, and then we will use the sawtooth to mimic the movement of the knob. Now let's use the connection line tool, and let's connect the pulse with the RC filter and the period with the sawtooth with the RC filter. The last component that we need is the clock, and that can be found uh, in the Modelica clocked subpackage. So inside the Modelica package, we have a clocked library, which is used when you deal with multi-rate systems, when you have different components working at different sampling rates. Like in process control industry, there are some actuators which are working at a slow speed, and there are some sensors which are acting at a very high speed. And if you want to integrate, so it's different type of multi-rate systems, we use the clock library. But for our case, we will only use uh, we will use a clock, the clock present inside the clock signals library. So clocked clock signals, and inside the clocks sub library, we have the periodic real clock. So let's use the periodic real clock here. Just to repeat again, it is present inside the clocked sub package. Inside that, we have the clock signals sub package, and inside that, we have clocks. And then we will use the periodic real clock. Right. So these are the four components that are needed to simulate this model. Now let's go ahead and give them suitable parameters. So for the clock, we want to have a frequency of 44.1 kilohertz, and that we will do it by setting a period of 1 divided by 44,100, right? And that is, as Leo mentioned, the medium sampling we need to hear the sound properly. Then for the oscillator, um, we will define we will have an offset of 0.001, uh, and this is because this pulse is fed as a voltage input to the RC filter, and we want to avoid the zero error, right? So Leo, correct me if I'm wrong. So we it's so I think that's the reason we are given an offset for this
Uh, no, actually, it should work with
with
without
zero.
offset. I
Okay.
think that we actually what we need is to offset in a little bit down.
Hmm. Oh, okay. So without the
But
offset, it will work. You
yes,
mean?
it should work fine
Okay.
without offset.
So let me just remove the offset then, and let's give it a try.
Oh, I think that the offset where you actually need it is in the sawtooth.
Oh, okay, okay, okay. So for the pulse, perhaps the only thing that we need is the period of the pulse, right?
Right,
And to detect um the sound, we need the period to be at least, let's say, uh, 80 or 90 hertz, right? To be able to hear something.
right.
Is that right?
Yes we need a frequency higher
Yes. So
than
let's take
20.
around 110 hertz. So for that, I will set my period as 1 divided over 110. So it's 110 hertz, and we can hear it, right? And then we will set all the other values as default, uh, right, Leo? Or
Yes, yes.
okay. Fine. And so that's the only thing we change here, the period as 1 over 110, which represent 110 hertz. And then for the
But we can
sawtooth,
design anything, Ankit, right? I mean, whatever we like as a pulse, different pulses can be designed here. For instance, over there, we had width.
oh, right.
So
Mm. So if you
we are
want to
saying
play
that we
around,
will like 50% empty, 50% full.
right. Okay, it's a good point. So let me just try to explain the
Mm.
default values here. So here, when we say amplitude of 1, we are the maximum voltage we are supplying is 1 volt. And then when we say width of 50, Uh, so for the complete period, this means that 50% of the time we have a false or a true signal. We have false signal, and for the 50% of the time we have a true signal. So that's the period, and we're defining what is the width for which the period is active, the pulse is active.
Right.
Yeah,
If we
actually,
say, if we say that is like one, then what would happen, Leo?
sorry,
100, I mean, for the width would
100. So
be
it will keep constant.
Yes,
right. Yes.
yes. Okay. So right, and then uh, let's give a value to a sawtooth. And as you said, Leo, for the potentiometer, we don't want the resistance to go to zero, else it will lead
Yes.
to short circuit of the circuit, a short circuit of the RC circuit. So let's use an offset here of 0.001. Uh,
Ankit, sorry to interrupt you. Helmut is asking why don't we need an amplitude? Because we need an amplitude, but we don't set it a different value. By default, we had that amplitude value as set as 1. So if you don't register anything, it will be considered as 1.
yeah, so we are considering 1 volt, and we are keeping the default value for now. Of course, depending on your circuit, you can change it on your circuit, but for this exercise, we're keeping the amplitude with the default value of 1, right?
Right.
Okay. And for the sawtooth, let's say we have a period of 1 second. So in 1 second, we go up, and then we go down. Then we again go up and go down. Right? Okay. Uh, I think this should be fine. And for RC filter, we don't have a parameter, so we will keep it as it is. Let's validate our model. Right. And as you validate our model, you could see that the model is balanced. So we are fine to simulate it. Right? Okay. Um, right. Okay. So to simulate this, I'll be using the Wolfram language to simulate this, because we have used a simulation center all the time. So let's try to simulate it using the Wolfram language now, right? And let's open Wolfram language so that we can simulate it from there. Uh, right. So in the in slide number 5, you could see that I already have um, this the function defined for you guys. Also, for today's session, I have updated a new notebook which with the ending as with the name as reuse and expand models with music, and that has all the result file as well. So you don't, if you just want to listen how how those circuit responds, you can just um, hear hear to the audio file, um, and so that's why some people might find a difference in this notebook, because this is a modified notebook and I've already shared it in the downloads section. Okay, Leo, so what we are trying to do here is we are trying to use a system model simulate function, and then we are passing in the model name. So let me just quickly verify if that is the model that we have. So in system modeler, let me go ahead and copy my model name. I will select it and then copy it. Go back to Wolfram language, and inside system model simulate, let me paste the model name, right? And after I do that, I need, when I do system model simulate without specifying which variable I want to store, system model simulate will store all the values. And as you saw, we have a sampler at 44.1 kilohertz. So imagine the amount of data that is generated. So if you just simulate it, even simulation center or Wolfram language will hang, right? So we have to specify which variable we want to plot, and in this case we want to plot the response of our RC filter. So if I go back to system modeler, you see we have this RC filter 1, and if I hover on the output, it says V. So we want to simulate the output of our RC filter, which is given by variable V. Okay, so in my model, let me change the name of the variable that I want to plot or that I want to simulate, and call it RC filter.v, and C is capital, right? RC filter 1.v, RC filter 1.v. Yeah,
You have an extra dot v. Yeah.
yes, yes, I removed it. And then I will set a time for my simulation. Let me set a time of, let us set a time of 20 seconds. And then we have this method automatic interpolations goes to 44,100. So using, when you use Wolfram language, you can set what is when you get the result file, you can set how many data points you get back from the Wolfram language, and you can set this manually. For our case, let's remove it. Even if you don't have it, it will work, and that's just an optional property. If you want to sample it at a higher rate, you can use that function uh, to simulate. And uh, let me delete and let me put it here. Okay, so once we have our model, we use system model simulate, we define the model name, we specify which variable we are interested in, so the data of only that variable will be stored, and then we specify our simulation time, that is 20 seconds, right? And once we do that, let's shift enter and let's simulate. So Leo, do you have anything to add up to this point, something that we should mention?
No, just that probably 20 seconds is a lot of time. You could reduce it to, let's say, 10 or something, but
Yeah.
it's fine. It went quick.
Yes. Okay, fine. So uh, right. So the thing is, this is the first time I started the system modeling functionality. So my system modeling functionality was loading. So the packlets that involved the system modeling things, they were loaded first, and now we are running the simulation. Right. I see there is a question. Uh, right.
Right,
Where do
Ankit. Yeah, where can we find users manuals for these modules, like the
like the
pulse, for
pulse or
example?
example?
Right.
Okay. So for the pulse that is present inside the blocks package. So here, if you go to the sources, if I select pulse, I can right click and click on view class documentation, right? And
Right.
when I do view class documentation, you have this uh, you have this nice diagram which where what the different parameters mean, those are displayed, right? You can so from this diagram you can understand what we mean by the different parameters. And you can also go to used in examples. When you go to used in examples, all the different examples where this component is used will be reflected, and then you
R-
can open any of those examples, simulate, and try to see how the model responds.
is there any other source, Ankit or Leo, you guys use to figure out how you can use these components?
That's why, but I usually check just the built-in
Right.
documentation. But I
Right.
guess that
Exactly.
the filter component that I made, it doesn't have any documentation.
Yes, because you want to encrypt it, and you don't want people to yeah. Right.
It was just laziness. I didn't
Right.
add any.
Okay, so Leo, now our model has simulated. Let's get back to Wolfram language. Now our model has simulated. Now the thing is, if I see what my RC test variable contains, let me write RC test and shift enter. Um, let's see what data is stored inside it. So here you could see we have a system model simulation data object, right? And this contains the data about the RC filter.v variable, right? So from this system model simulation data, we can also ask for a audio file. So this object has that option of providing you an audio file from your simulation results. So now let's use the option audio by putting it under the square parenthesis, square brackets, and then we can specify the variable name for which we need the audio. In our case, we need the RC filter 1.v. So let's copy it and then put it inside uh, the curly parenthesis, and let's evaluate. Right, right,
Yes.
fine.
While
And then
waiting, maybe I. Okay. I'm sorry.
yes.
Go on.
Okay, let's finish this with that.
Mhm.
Then we can take the questions. So now, once we use this audio option and we provide the variable name that we want to plot, we could see that it gives us the sound object. And then if we click the play button, perhaps you should be hearing some faint sound, right?
We
Yeah.
hear it very, very low, almost
Yes,
no
Right.
sound.
yes, and that is something I did knowingly, because sometimes for some audience it might be too loud and it might create chaos. So that's why I have provided the files with the sound clips, so people can actually hear at their end. And please, when you are playing the sound, have your sound levels down, because when you're experimenting with sounds, some sounds might create an headache. Like Leo the oscillator one did cause a headache for me, but one has to be careful. So when you before playing the sound, try to make sure that your sound levels are down and then try to hear it. So I'm just warning you beforehand, right? So yeah, so once we create our model, we can use the system model simulate function, specify the variable we want to store, because the result file is very big, specify the time, and then use the system model simulation data object and use the property of audio and pass on the variable that we want to create an audio from, and then you have the sound file here, right? Okay, with that, now let's take the questions if you have any.
Right. I was gonna. I forgot what I was gonna ask.
We have a
Uh,
question: how to increase text
yeah.
size in the translation view, right? So let me get back to model center. Where is he? Yes, here. So in the translation view, if I open my translation view here, let's say if I want, let's say I want to increase the zoom level of this. So I press Control in Windows, and then I use my scroll wheel to increase or decrease the zoom levels. Perhaps it is Command and something similar in Mac. So that way we can increase or decrease the values. Okay, Carl has
And
a
and
question.
I think it's important that that works in other places as well. For example, to
Yes.
change the size of the icons, text view, etc.
Yes, so in the icons as well, if I scroll up, you could see the icon size has gone up and gone down. But the names, the text size of the component names, they are defined by the system settings, so that we cannot enlarge. So those some of those settings cannot be changed, but in other cases, you can just press Control and use the scroll wheel to zoom in or zoom out. So Leo, I think you can answer this. There is a question where we have like, can you see the time domain plot and frequency domain plot (FFT) of the output signal?
Yes, you can use the spectrogram function in Mathematica. If you, I think that you just need to pass the audio object and call the function spectrogram.
Yes. So let me bring it up. Uh, I will bring it up in a minute. Uh, that I'm actually opening up the blog which Leo wrote and has that spectrogram in it. Right. So Leo, this is the blog, right? Which uses the components that we are seeing here. And
Yes.
here, if I scroll down, I have my simulation done. You have the time series plot, and then you use the spectrogram of the RC audio. So let's try to do it.
Can you increase the font? Just to show it better.
Yes. Yes. So then you can call for spectrogram of this audio. What do you say? Let's give it a try. I don't know how it would look like, but let's try. Um, but what so spectrogram of it should take the time series values, right? The spectrogram.
I think it can take the audio object. Let's check. So just assign it to some variable.
Okay, so maybe yeah, I'm just assigning the output to A and then spectrogram of A. Let's see.
Oh, so it's I think you passed a list. So to get the first.
Yes, let's try. Yes, so we see a spectrogram, Leo, and perhaps you'd help me understand what this means.
Yeah, I think that it's better if we manage to hear the sound. If we hear the sound, it will make more sense.
Can you hear it?
Yes, can you increase it a little bit? Is it on your side to control
Yes.
it?
Let me try. Can you hear it?
Yep,
Yes.
it worked.
So what we're hearing is that the initially we have the pulse wave, and then the saw wave makes like this. It produces like a. Okay, so how to explain it? It's a little bit like how in a piano it's made. When you press a key, we get like a burst of sound, and then that sound fades a little bit.
Right.
And here work it is like a very rough simulation of that. We
Yeah.
have the filter completely open and then gradually closing it. And so we can hear like these pings, pung, pung, pung. So what
Yes.
we see in the spectrogram is each of these pins. Uh, so we have the main sound, which is like these spikes that we see, and we
Mhm.
can see that the frequencies are gradually fading out, especially the higher frequencies, which you can see in the top of the spectrogram, and we
Right.
keep the low frequencies.
Okay. Right. Okay. So
Yeah.
Leo, is there another way of visualizing the result? Because is spectrogram very much limited to the audio guys, or like do you also see the FFTs of the time series plots?
I mean, this is an FFT. The spectrogram is the FFT, but changing in time. if we use like the regular FFT,
Hmm.
we will have to pass like a small chunk of audio, and we will see the frequency content of that specific chunk of data. But the spectrogram displays it like over time.
Right.
So we're basically seeing what's the FFT over time.
Yes. Let me simulate this model for 1 second now. And
While
well,
waiting for that,
yes. Yeah.
yeah, I have a question for Leo. So, Leo, is there any difference? I mean, can we do any filter modeling in Mathematica, or if we can, is there any difference between filter design by using Mathematica and System Modeler? Which one would you prefer, and why?
It depends on the application. For example, with Mathematica, there are a bunch of functions that we can use to generate to design fixed frequency filters. So these fixed frequency filters are used in certain applications in electronics. However, in audio, what we need is variable filters because we are changing how the sound behaves.
Right.
So it is usually like like simple filters, but that can change their properties.
I
Right.
see. I see.
Also, Leo, what I did now was I simulated our model, and once I simulate our model, this is the FFT and this is the time series plot that we're looking at, right? And let me try to do it again so people who are following your discussion, they know how to do the FFT in system modeler. So let's start with a blank window, and let me open uh, a blank plot. So let's say, uh, so as Leo, you rightly mentioned, spectrogram is a way of visualizing the results as a FFT that changes over time, right? Uh, right. And and there is also a way where we can look into the frequency response of a time series data in the in simulation center, right, where we view all the results. So okay, but for people who are new to this terms, so when we plot a variable in simulation center, you are looking at the values of the variable as it changes with time, right? And this is the time series data, right? And this time, and but in some cases when you deal with let's say music, where you're more interested in the frequencies, or you're doing vibration analysis where you deal with frequencies, then looking at the time series data perhaps doesn't tell you all the picture, or perhaps it is not easy to diagnose different things, right? And perhaps it's better to visualize the results as a frequency response. And to get a frequency response, uh, let's see how we can get a frequency response of this variable. To do this, we'll go to Tools and then select FFT Analysis. So Tools, FFT Analysis, and here it tells me drag and drop a variable here. So whichever variable I want to analyze, I can drag and drop it here. In this case, I want to analyze the output of my RC filter one .v variable. So let me just drag it and put it here. And then start time is 0, time end time is 1, and there are various other options like remove DC component and other resolutions and other things. And let me click OK. And now once the FFT has been done, I can zoom in into the interesting part, and we can see the results here. So here, Leo, you could we could see that for our sine curve, uh, or our pulse had a frequency of 110 hertz, right? And if you look at the result, we have the the peak of the peak frequency at 110 hertz, right? So you can see those values easily using such plots rather than just seeing the time series values, right? So Leo, do you have anything to add to what I said?
Yeah, just the values that we are seeing after are the
Hmm.
harmonics. So the second should be around 220.
Hmm.
Oh, it's actually 300. Yeah, it should be
Times higher.
330, I guess.
Yeah.
330 to
330,
220, 330, etc.
330, and yeah. Okay, but anyways, Leo. So this is also because a lot of our audience are not electrical engineers. So let's try to keep it on the top level. So you can visualize your results in a frequency domain as well, and then try to understand your system, right? So that is also possible. Okay.
So what type of advantage we will get out of it, Ankit or Leo? So why one should look at that? So
So Leo, so Vedat, as you mentioned, we saw the detailed model of a gearbox yesterday, right? So
right,
imagine there is a failure in one of the tooths in the gearbox, right? And when this failure point arises, there is some event that is triggered, and since it is rotating, there is a frequency involved, right? So
right,
looking at those frequency curve, perhaps we could figure out which number of teeth is broken, right, from vibration analysis.
right.
Those kind of that comes to my mind. Perhaps you
Yeah,
have a different
yeah.
picture, you have a different story.
Yeah, yeah, you answered really well actually. So yeah, by looking at, we can just figure out whether we see the expected behavior. In a way, if we see unknown harmonics over there, unknown frequency characteristic, then if either we can say that in a like a rotating machinery, we can say, oh, there might be something faulty. So by looking at those values, we can also maybe pinpoint if someone at some point somehow characterize it. We can say, oh, okay, this fault can be, let's say, between planetary gear and a three-stage gearbox. So reading those really help and understand what type of faulty system we have. So those are quite valuable tools.
Right. So let's say you have a motor that is operating, and you get the frequency measurements from the motor's outer body, and then you have a model of it in System Modeler. You could simulate and then try to compare the frequency response of what you got versus what your model tells you, and then perhaps you can use it to troubleshoot. Um,
Right. Carl here is saying that it's a square pulse, odds harmonic only. Like for instance, yes, Carl and Leo, if I am wrong, please correct me. So if we see, let's say, they're not the odd even harmonics, then we could, uh, which we shouldn't see, and then we could come up, oh, okay, something is wrong. So just by looking at, it will hint us whether we are doing something right or wrong.
Right. In this specific case of the audio, the square wave or the pulse wave, it has only uh, even harmonics, but other waves have like even and odd combinations.
Right.
yes, and of course, if you right click and then go to properties, you can actually view it as a logarithmic scale as well. And logarithmic to log 10 or log 2, those kind of logarithmic scales are also possible. But Vedat, I think we are going too deep now. So let's get back to our presentation, or to our model. So far, Leo, we saw how why we used a periodic clock to define the frequency so that we can hear the sound. You told us that we need a pulse that should fluctuate, that would oscillate at a certain frequency, and that frequency should be perhaps more than 60 or 70 hertz so that we can hear it. It's a task for our audience. Try with a frequency less than, let's say, 50, or less than 20 hertz, like let's say 10 hertz, and then try to simulate the model. So change it by 10, and try to see if you can hear some audio from your model response. And if you hear a model response, do let us know, because then we want to interview you, because that that will be very odd. uh, uh,
If it is possible to hear, but what you will be hearing is the higher harmonics. Like in the case that we measure 330,
mhm,
so that second harmonic, which is still quite large,
mhm.
if you lower the frequency, it just displaces a little bit. So you will not be hearing the fundamental, but the second harmonic.
Okay. Yeah. Thank you. Thank
And
you. Thank you, Leo, for I will add those under the terms and conditions.
Right.
Um,
Ankit, before going on to the next level, can you just show how to drag and drop the RC filter to the FFT?
Yes, sure. I will show it again. Um, so I will go to Tools, FFT Analysis, and then uh, I will click on the variable V, and then just by by keeping
You
my
will
left,
hold it.
I will hold
Mm.
my left button in my mouse, and then I will drag it to the drag and drop variable um, button here, and then just remove it, and then you could see that that has been recognized, right?
Right. Other than that, we had the logarithmic view. It doesn't matter which FFT we have. For all FFT, we can
Yes,
have logarithmic view as well.
yes,
It
yes,
is base 10 and base 2, right? And
yes. So if I and to set it, I can right click, go to properties, and then in y-axis under the scale, I can change linear, log 10 or log 2.
right.
I can change between them. Okay, with that, let's get back. um, since it's already we have already consumed a lot of time up to this point. uh, so let's quickly go over the other models that we had planned, so that our audience can then try it after the session is over, right? So Leo, we see that in step 2, so I'm referring to the solutions folder and the step 2 model inside the solution folder, right? So Leo, we see there is another type of filter with uh, components like amplifiers and other things. Like, what is the advantage? Like, why can't we just use RC? Why do you have two different designs for the filter?
yeah. So the first one, it's a single pole filter.
Hmm.
What that means is that it's filters, but it's not very good at filtering.
Okay,
So this other design, the silent key, is a second order filter. So it's basically twice as good at removing frequencies,
right,
and it in practice it will produce like a smoother sound.
right,
And in synthesizers, there are also very common fourth order filters, which even filter more.
right. So when you say it will produce a smoother sound, let's go back and try to hear the sound that it produces. I'm not going to simulate it again, but let's only hear what it produces. Can you hear it? So it is somewhat smoother than the one. To be frank, I cannot distinguish uh, like by my ears. Like, it's very hard, but I go by your word, Leo, that using that perhaps it's much more smoother, right? Okay. The next model, Leo, that we had was an oscillator. Like, why do you need this model? And if I go to step 3, I have the oscillator component, and if I double click, I see this IC circuit and other things. What is all this?
So that's I mean, once you want to build the actual oscillator, we don't have the advantage of dragging and dropping a Modelica model in real life. So we need to build it using other components. And here there is a simple model of a very common integrated circuit called the 555.
Mhm.
So that's a very old integrated circuit that can be easily obtained, and it's possible just by wiring it this way to generate an oscillator and get like this pulse wave, or in this case, I think it's a saw wave.
Right. So Leo, you have models of these things that you use before you create your own modules, right? So you create this oscillator, and then you tested it, and then you create your own PCB or.
Right. In this case, the cool part it was that the actual integrated circuit
Mhm,
is made out of a bunch of transistors.
mhm.
But this model that I have here is a behavioral model. So if you open it, there are no transistors. It is basically code, Modelica code that behaves just like the original integrated circuit.
Right. So basically, you have defined which are the components that are needed, and
Yeah,
for
the
these
inputs and outputs.
components and yeah, inputs and outputs, and for those inputs and outputs, based on the different state, you are creating your own triangular or timer, uh, like that, right? And this is
Yes,
something that you created uh, custom because you had a custom need for it. uh,
yes. This component didn't exist in Modelica library, so I made
yes.
it.
And the thing is, you made the component once and it has been several years and you have been reusing your component, and we have been taking advantage of that and reusing it in our course as well. Okay, fine. So let's try to hear it. And I want to give a disclaimer. This audio doesn't sound good.
It's not true. It sounds beautiful.
Sounds beautiful. Okay, let's
Yes.
let's let's play it. Sorry, did you hear it, Vedat? I don't like it, but Leo,
No,
maybe it's beautiful for you.
I kinda like it. So Leo, I am on your side on this.
It sounds like the like a toy gun that I had.
R-
Choose
right,
laser.
right. I felt like I am playing Atari.
Okay, okay, right. Okay, Leo. So far, if I go back to my model, we saw a filter. Then we saw a different model of the filter with operational amplifiers. Saw you created your own oscillator by creating models of the your IC circuit. And then in step 4, we have something called an envelope. What is an envelope? Because and I have selected those components because I could not understand what those were. So if you can tell us for our audience, like, what is this envelope and what you're trying to do here?
Yeah. So basically, when you are trying to imitate a sound
Hmm.
using electronic components, the real sounds have variations. For example, the amplitude. Going back to an example, a guitar, when you first pluck it, you have like a loud sound, and then it starts decreasing.
Hmm.
And an envelope is used basically for that, in order to generate a sound that is like high in the beginning, and then we can control the amplitude. We use
Hmm.
that signal to control the amplitude and make it like decay
Oh, so
as a natural sound. Yeah.
that's what we are seeing here. It goes up and then it decays, and that is the thing that's this component is trying to create,
Yes.
right? Okay.
And yeah, and that one is connected to the other component, which is it's a voltage control amplifier, which is basically a multiplication, right?
Yeah, because if I go inside, I see that you just are multiplying the sine wave with the envelope that you have. So it's just a simple multiplication that you have here.
Yes, it's just to control the sound, the level of the sound.
Okay, so let's get back to our notebook, Leo, and let's try to hear how it sounds. Okay, it feels like a uh, right.
It's like a little bit like a xylophone, like ding, ding, ding.
Yeah,
Or here in Sweden, we have while like crossing roads over their pedestrian roads, we have that kind of sign which tells you it is time to pass. Otherwise,
The direction lights of my car
right?
as well.
Yeah.
okay. So, Leo, we saw some basic components, and walk us through, like, using those components. Like, once you had created a component, you verified its behavior, you checked the response of the different blocks, and using all those blocks, you have created something over here. What is it like? What does this model tell me?
So we can see that there are different sections of this model.
Hmm.
I have one called bass, which is it produces a bass sound.
Hmm.
Then we have the hat, which is like a percussion, like
Hmm.
cymbal percussion, and the kick drum, which is like a boom, boom, boom that makes
Hmm.
the electronic music. And just combining envelopes, oscillators, filters, it is possible to create such kind of sounds. Probably the simplest is the hat, the cymbal sound,
Hmm.
in which we take noise that you can see in the block there.
Hmm.
and then we are controlling the amplitude of that noise with the envelope, and so
So,
it produces like a small burst, like pss, pss, pss.
so Leo, our our users have not seen the noise component yet, and I could see that it says normal noise with an expected value and standard deviation. Can we also model noise in system? We can of course model noise in system modeler. So what are the advantages of it, like, and what are the different types of noise that you typically use in in your circuits?
Yeah, in general, for the electric circuits, I usually use the normal noise because it's the one that you get
Hmm.
from in electronic components, which
Hmm.
is the normal is that like the uniform distribution, so it has like the same uh, amount of power, not matter without matter the frequency. But
Hmm.
there are other kinds of noise, like the Gaussian noise,
Hmm.
in which we have the like this bell. So in the
Hmm.
center, there is larger probability of getting a value in the center, and the
Right,
extremes are less they
right,
have a lower probability. So it all these kind of noise are very useful for different applications. But in the case of audio, most of the kinds of noises work fine.
right. And for our curious users who want to know where this noise component comes from, so it comes from the blocks package inside Modelica. So if I click on the blocks, we have the noise package here, and here you could see you can have a global seed, and there are different uniform noise, normal noise, truncated noise, and band limited white noise. So those are the four noise that are available that you can make use of in your models. Okay, Leo. So now you created components, you mixed them together and created some music, as you say. Let's open our Wolfram language notebook and try to see how it sounds like. So let me open it, and then okay, let's play the music. That was cool. That is the music I actually enjoyed. But
It's,
yeah,
is going to be my next Grammy.
okay. All the best. Uh, so okay, um, and as we and as let's get back to our model. So now, as Leo, you said you have identified the three big components in when you create this model: the bass, the hat, and kick drum. Uh, Perhaps the next thing that you would do is create blocks, uh, and then try to reuse it in your future models, right? And uh, before we conclude this part of the presentation, I wanted to show a quick way of creating uh, those blocks. So in the last uh, two sessions back, we saw that we created a new model, we dragged in all the components, we created an input, we added parameters, and then we had a component, right? But
Right.
there is a very fast way of creating a component as well, which I didn't show up to this point.
Oh man, you need to show us.
Okay, let's say we have this component, and I want to this different components, and I want to create a new block out of it, right? I want to create a new component out of it. So what I will do is I will select my components that I want to transform into a block, or a new component. Once I have all the components selected, I will right click, and I have this transform into new class option, right?
Okay.
Select what you want to do, what want to convert, transform into new class, and then I can give the name of what the new class should be called, and can give it my bus. I give it a name, and I can insert into. So I can put this new component anywhere I want to define, right? So let's say I want to put it under my components package. So I will remove solutions and write components instead.
Right. How do you know we had components?
Mm, because I created this package.
You created, but is there a way we can check that, Ankit, also, where we can put visually?
Yes, but when I'm in this mode, I think I cannot scroll.
Okay,
My,
okay.
my, my, my view is locked. And then let's click OK. And here inside the components package, you could see my bus
It's
component is
created.
created. I will double click here. And of course, I have to do some styling because it created a raw component for me. And
Mm-hmm.
once I set my boundaries and I double click to zoom it, you could see that my new model is created. I can go to the icon view, place the output as I want it, put it a text, uh, and then my component is ready to be reused. Uh, Not yet, because we don't want to be lazy, and then we want to document it. So I will press F1 and then go and edit in the what you see, what you get editor, and write document about the component. And for now, I am lazy, so I will just write my new component and then get back to the view and then write description for my class, and then I can reuse it later on, right?
Right. Also, Ankit, when you do this, we also got all the parameters for those corresponding component inside.
Mhm.
Right? We didn't need to set those parameter again. Whatever we had.
Yes, it is also translated, transported to this
Right.
view as well. So yeah, those things are carried forward. So right, so let me get back. So here you could see that once you know that once you have identified that this particular set of components you could reuse somewhere else, you can create a new class from it and then create some tests around it, and then you can create your own reusable uh, components, or you can create your own library, right? Okay, Vedat, I think we have covered what we wanted to cover for this section, that create, reuse, and expand models. But
Okay.
there is one very important thing that I have actually not covered in this study group yet. Like
Okay.
how do we create a library? Like
Oh,
we all use the modeling principles library that I created, and then we have never seen like how do I create one?
yeah, we need to reach out to Ankit then.
No, no, no.
Whenever we need.
No, there is a easy and quick way. And let me teach you so that you don't have to reach out to me. So let's go to File and New Class. So this is the new class window that you have guys must have seen at one point. And here under the specialization category, we have different options like record, connector, package, and other things. The only specialization that we need to care about at the initial modeling stages is the package specialization, right?
Right.
So once we write the package specialization, you could see the icon has changed to a package structure, and then you can also also change or choose between different types of icons here, right? For now,
Okay.
let's take the default icon and then give it a name, my new library, and then click OK, right? And you could see that my new library is now created, and then inside this I can right click and create a new class in my library. So when I right clicked and I selected new class, you could see in the insert into we have this name of our package, my new library. So whatever model I will create now will be inserted into my package, right? And
Okay.
using similar method, you can create further sub packages inside a top package, and then you can create your own libraries.
I see. So can you create us just two of them to show how those new sub packages are listed?
Okay.
placed in that?
So let's try to repeat the process so people can remember. Right click, new class in my library, specialization, select package, and let's write components, right? And
Right.
then we will select a a suitable icon and then click OK. And then let's say we want another package for our examples. So right click, new class in my new library, specialization goes to package, and then uh, perhaps
Examples?
examples, examples, and then
Right.
select an icon, examples, and click OK, right?
Okay, great. So maybe we can also try to create a model inside the examples to
Yes.
show
Also, one
how.
more thing with that, once we have these components and examples inside it, I can select, I can left click on my mouse, hold it, and then I can rearrange my
Right.
packages. So let's say I want examples to be first and then components. So I can select and then I can drag and put it in between those two sections, and then I could rearrange it, right?
I see. I
And then
see.
inside my example, inside the examples, you said we want to create a model. I will right click and new class in examples, model, and then we'll say my example here.
So here we pick the folder we want to put in, right? I mean,
Yes,
which
yes,
model we want to create and where to put it. So we need
yes,
to pick the corresponding one,
yes.
not
And
my new library.
yes, let's say I want to change my example to my new component, and I want to insert it into my components package. So in this case, I can actually select my components and drag it inside my insert into thing,
Oh,
insert
we
into
don't need
option.
to remember every time how to write all those
Right,
addresses, right?
right. So you can just drag it here and
Okay.
then click OK, and then you could see that my component is created inside the components package.
Right. And one question: why are we insisting on term library, Ankit? And why not call it package?
Hmm.
It is a bit philosophical question for a modeler, right? I
Uh,
mean, to me, it depends per modeler, the modeler, I would say. But to library here, we are saying that it, let's say, serves to a certain goal, like rotating machinery library. What we are saying that we have a package which tries to solve problems related to rotating machinery, and related to all those problems are gathered under one package. That is why we call it library. But
Perhaps Leo has a better answer
yeah,
because Leo.
No, I don't have a better answer. I guess that is just legacy naming.
Yes. Okay. Before we conclude this part, Vedat, there is one thing I wanted to show. Like if you go and right click and save the package, so there are actually two different options: save in directory structure and save in a single file. Right? When
what
I
are the differences?
so when I distributed my package uh, in the download section, you could see that only there is only one file, right, which says Modelica principles.mo, right? And so all the different components are present in one single text file, right? But imagine you are working in a big group with different uh, different library developers working on different sub libraries, right? And then you would
Okay.
want different files for each of the different packages, so that when they make some changes, they only commit to that package and not to the others, right? So there will be no clashes. So to enable working in big groups, it's better to save it in directory structure. Also, it is beneficial, let's say if you're hosting your package in GitHub, then it helps you in understanding, okay, you made change in this file or this particular model, and then you can easily track it. So when you have it in a directory structure, each package is has its own files, so they're distributed, but several different files are created.
I see. Yeah.
But when you use it in a single file for a simple model, it's fine, right? Everything is in one big file. But as you start doing more bigger projects, it's better to save it in a directory structure.
Okay. Is there any possibility to change a single file to library later on? Is it like a one-time decision?
Um,
Which I haven't tried. I noticed that now. While just what I do every time, I just duplicate it and save as differently.
I'm not sure actually. Um, I think yeah. Okay, so let's say you have this library saved as a MO single file right now.
Right.
Uh, it is possible to change it into a directory structure at a later stage. So let's say I save it as a single MO file in my desktop, and then I will right click, and then uh,
What
So
I
you
will
have
duplicate.
and then with that I will not duplicate it. Let's say I
Okay.
changed my mind and I want to save it in a directory structure now. So I will right click, and then there is an option called split merge and save, right? And if I click here, you could see I have now this option, save in directory structure, and then I can save, and then it would create a directory for me. And if I
Okay.
go and if I open my directory, it opened in a different section here. So you could see for every component I have different files. So this enables
Right.
me that if I edit one of the files, I only save that, right? So it makes it easier for me to have control
I
um,
see. Yeah.
over files. Okay,
Yeah.
Vedat,
I have also learned another thing.
okay. There is one more thing actually I want to cover, which I think will be very beneficial for our audience. Um, so there was a question you remember Vedat yesterday, that um, can we store a particular variable in Excel file, right?
Right.
So when we go and go to file and export, and we select result as CSV, all the different variables are stored in the CSV, right? And we don't want that. We in some
Mm.
cases we just want only to be able to save one or two variable in the Excel file, right? And in order to do that, I said there is a way which I could not recollect yesterday because we don't use it that often, but I looked it up, and there is a very easy way of doing it.
Oh,
So let's
really?
say
Yeah.
so let's say we have plotted our RC filter 1.v here, and this value we want to shift to an Excel where we want to do the post processing analysis, right? And in
Okay.
order to do that, we will right click here, and there is an option, copy as data.
Oh,
So let's select that option, copy as data, and let me open up Excel. Uh, yes, and then if I paste it, you could see the time values and the filter values in the SI unit. Those are copied in Excel, and you can and if you have multiple variables in the plot, then also this works, right?
okay. Okay.
So
Yeah.
I told you yesterday that is an easy way. I was not able to recollect it, but yeah, but you see this now.
Yep.
Okay. Um
What else? Yeah,
I
Ankit,
Mhm.
can you quickly tell the difference between tell me what the partial class and package is?
hmm. I think Leo can describe that better.
sorry, can you repeat the question?
Yeah, what is a partial class or packages?
Oh, okay, we're getting into dangerous territory. So I guess that this will go into a more advanced Modelica language class. So it's it's like a different way of reusing parts of your model. So let's say that you want to create a package or a component in a subsection of it. You want to use it on multiple models. So there is like this way. You can say like my model is partial, so it's not complete. So don't do
Okay,
not try to simulate this thing because it's not complete. And then from this is your base model, your partial model, and then you can create other models that take that partial package in complete it. That way you can like create variations of
I
this
see.
model that shares like many common things.
Like, so with that, you can think about it like we have a chassis and we have different
Exactly.
and we have different bodies on top of it. If you do some changes in the chassis, then perhaps the other things that are inheriting it will be will not like it, right?
Right. The car,
So
car won't start for sure.
car will start. I don't know where it will go. Uh, okay, right. Okay, let's get back to our presentation. Um, uh, right. So, fine. Just to conclude on this section, once you create a model, you find a component which is repeatable. You can create a reusable component out of it, and then you can create your own libraries. Right. Okay. Just to summarize what we have seen up to this in this section, that when you have large models, it's better to split them into smaller models, and these smaller models should have one function so that you can repeat it at different in different other uh, models. And then once you create this small component, it's good to create tests for each component. As Leo said, he understands how his RC filter works. He understands how his filter with an operational amplifier works. He understands how his oscillator works. As he now understands all the different components, he can plug everything together and then he can scale up, right? So rather than creating a big model, try to come up with simple models first, test it, and then scale up. Right.
Right.
Okay, Leo, I think you're typing. I can hear your audio. Uh, okay, so with that we conclude all the different guiding principles that we thought we would cover in this study group. And just to summarize what we have, let's summarize or get an overview of what we have seen so far. So
Right. Right.
we started with an let me create a text cell here. Yes, alt 7. Yes. Okay. So in the first two sessions, we started, we used the coffee mug example to get used to the way of thinking about components, and then we could plug them together, and we learned how to initially start using system modeler, right? Then we analyzed, once we have a model, we want to analyze for different parameters how the model responds. We want to calibrate, we want to see uncertainty. And for those things, we saw how we can integrate our models with Wolfram language and test different scenarios, right?
Right.
And
It gave
following
us
the,
some certain advantages, right? To use
yes,
that one.
yes. As Leo showed, you can have spectrograms. So the thing is, we have a lot of functions in system modeler, but there are other things that you can do. You can have a
Right. For instance,
spectrogram of,
control design, right? For instance,
yes,
I mean, in real life, one can just can sit and try to figure out all the state variables for, let's say, a gimbal, or maybe, I don't know, camera stabilizer. So there are so many variables. Instead of doing that, what one can just model that thing on system modeler and get the Mathematica. We have, for instance, one magical function, system model linearize. You can get all the state variables and then design your any kind of controllers, which is like state space controller, and ship that controller back to the system modeler, which you cannot do on system modeler alone. So that kind of combinations, integrations, show superiority of the Wolfram language, right?
right, right. Uh, and then with that, once we saw how system modeler and Wolfram language worked, when we got used to it, then we saw different guiding principles. Like we should start simple so that we understand the system first. And then we do not confuse ourselves, right? And then once we start simple, then we start learning from other domains, because when we start, okay, so when we start modeling, we start with a basic model. Then you will get stuck at points where uh, you don't have an analogy of how do you model a phenomena, right? Or how do you model a process? There is nothing analogous in your domain. So you would start looking at other domains and try to see, is there something similar that we can use
Right.
in our domain, right? And then we saw, uh, if we are just stuck in our domain and we don't take care of interactions like what is the thermal uh, uh, like can things interact thermally, like if there is a mechanical thing connected to a electrical system, how can both of those system interact? And when we create a model, are we being aware of those interactions? And if we can model it, good enough. If we are not able to model those interactions, are we listing those assumptions in our model, right? So those things are,
Right.
are crucial. And then once you start creating your model, you Leo has put so much of his logic into his RC elements, his silent key, or his operational amplifiers, and at the end he's so confident of his model that he has fallen in love in his model. And when he tries to create his own PCB circuit with his models, nothing works. And then he's complaining to the PCB manufacturer that your there is something wrong with the PCB board. My model works, right? But perhaps Leo might be missing some of the intricate behaviors of some of his components that he might have missed, right? So one should be staying critical to their model at every stage. And then stay critical about your data. There are various interpretations of data. So when you get data for model calibration, check the metadata, check if there is no calibration error, or if you're using data for parameters, try to calibrate and see what you got from the internet, like the thermal conductivity value of a particular material. Try to verify it. Try to see if there is any variance, right? And then we also discussed that when you see a data in real life, try to, if possible, try to create models and try to see, uh, can you justify the response that you are seeing in the data, right? And through that you can try to understand the process.
Right.
And then we saw yesterday how to use different models, because different models have different modeling objectives, right? In one case we want to model failures, we want a detailed model. In some case we want to model interactions with the grid, so we had a more engineering model. And in one case, we are just interested in the business use case. So once we know how much available power is there, how much actual power we can retrieve, we can add those inputs to some financial values, and then we can look into those financial aspects of a system, right?
Right. Right.
So depending on the different modeling objectives, we can use different models.
Right.
And finally, today we saw Leo showed us some of his models that perhaps he has developed 7 or 8 years back. And today, even after 7 8 years, we were able to use those models in our session today and try and learn something um, uh, about music and how to generate audio, right? So you could see how these principles help us in our modeling journey, right? um, yeah, so that was all from my side. Vedat, do you have any comments that you want to uh, pass?
Right. I mean, what we try to give is mostly we wanted to show how, as a modeler, we think, right? I mean, we start simple and we try to test them, and then it's like a building a wall, brick wall. We continue brick by brick. We try to understand it. Uh, then also depending on our objectives, we design models in a way that serves those objectives, like a wind turbine model. First, we interested in really high fidelity model in which we are mostly interested in what is happening in terms of vibrations. But then we simplified it because we were mostly interested in that time only the grid related, how much power we can produce and harvest and deliver to grid. Suddenly, all those complexity related to vibrations disappeared. Uh, Other than that, we show usability. I mean, which is really powerful way of modeling. We just model that thing, and then we saw that that thing it is not just a single time use case, right? If if there's a possibility in a way that it is similar to another type of component, we can use that generic base class and use again and again by just changing the parameters. So it keeps our canvas and the minds clear by doing so.
Right. Vedat, let's also, like, once we have, as you rightly said, we saw the different guiding principles and their usages. But let's also give a brief, um, like, some help tutorials, like where
Right.
people can refer to if they have more questions, right? So for that, I created this Learn More notebook, which is also shared in the download section. So first thing was, if there we covered only a small aspects of system modeler, and there are a lot of new other features that would be helpful depending on the domain that you're working in. And the best place to look at it is at our what's new page and our features pages. Also, the resources page is very helpful. There is one thing that I wanted to point here. As we have this study group, we also had a study group for engineering, like in 2021 or 2022, and some of those sessions are really useful. Two sessions I want to highlight from this. If you have time, just watch those two sessions and it will be worth your while. First is connecting to real world applications, given by Leo, where Leo goes into, like, how do you connect your models with sensors using Arduinos? How do you connect to real world sensors like PLCs using OPC standard, OPC libraries? And Leo also goes through, if you have an external C library that you want to couple with your models, how can you do that? And those details you could see in the connect to real world applications session here. And also we had a session on introduction to Modelica, and this is me with more hair at that time. But you can but in that session we go into the very basics of the Modelica language that we have been referring to on and off, right? And there we have gone through, like, how to declare a parameter, how the equations work, what are the different events you can have in your models. So that is a good place to get an introduction to Modelica, right? And if you are interested in any other modeling domain like thermal modeling, biological modeling, it is a great place to look for resources, right? And I would highly recommend for watching those sessions for people who are really interested in integrating with sensors. That is a very good place to refer to.
Ankit, can we share those links?
Yeah, this notebooks are this notebook is already there in the download material, and one can download it from there. And then about Modelica, from my own experience, I have tried to provide a comprehensive list for people who want to learn Modelica. The advantage with Modelica is it is a open source language with a very big uh, community
Community.
working towards standardizing the language, right? So it's if you're interested in modeling physical systems, it's a very good language to learn. And here I have all the different resources that will be useful. Then we had questions on how to work with data, and here I have listed the different references that we have when we work with external data, external C code, or exporting data from simulation center, and so on, right? So you have all those resources here. And then uh, troubleshooting is very important. With that, on one session we had few errors, and you
Right.
could see, once you start getting errors, it takes up a lot of your mind space, right? You are completely involved, completely in a chaotic mood. and,
Exactly.
and then
Exactly.
and then you start searching which is a good resource to start troubleshooting, right?
Right. I would recommend the Modelica by examples to learn the Modelica, what and to see how the equation systems work, like uh, how the flow and the potential variables. While people are creating such components, they can learn about what they should pay attention to initially, step by step, by testing the examples over there. Also,
Mhm.
they can learn from them.
Yes.
Uh, yeah, it comes over time. I mean, it requires a bit effort to comfortably debug their models. uh,
Yes.
yeah,
And
but it
also,
works. It definitely
yes.
works.
And also we have different ways, like we have something called equation browser, which is an advanced concept that we have not covered here. But here, if one really wants to go into the equations, how those things are solved, it is a more mathematically um, advanced thing. Uh, so here one can see the incidence graph, how the different equations are solved sequentially, one after the other. If you want to go into the nitty gritties of how the equations are solved, then these are the nice references, and everything
Right.
has been mentioned in this document, so people can refer to it in their free time. And then if you want to share your models about the FMI standard and how you can create installers for your libraries, all this um, good resources are listed here, right? And uh, we covered a lot of models using the concept of system dynamics. So the business simulation library uh, is based on the system dynamics metaphor. And if you want to keep creating those kind of models, you would need some reference examples, right, that you can use and follow. So there are three books called Systems Zoo from Hartmut Bossel. So this is one system model, System Zoo 3, 2, and this is one on System Zoo 3. I don't have the System Zoo 1 with me, but those are really good books, and they have very simple examples that one can start modeling and trying to understand, right? And along with that, there is this nice book on business dynamics by John D. Sturman, and that is also a very good book that covers the introduction on system dynamics. So this is how the book looks like. Those three are the um, are good resources. And yeah, and then upcoming events. So if you have liked the events or the study group so far, we have some upcoming events that would be useful for you. So we have one event on handling uncertainties and calibrating models using Wolfram language. This will be taken by Sergio, and the dates will be in the upcoming months. The Wolfram U team will get back with those dates, and then we will have the new system modeler released, where hopefully I will be presenting what are the new features in the new version. And then we have an aircraft library which will now have components that can be used to create drones, and we will have a presentation on that. And then Leo here has worked tirelessly over the past few months on his electric circuit course, where he will go through all the nitty gritties of his components, and then along the way he will teach you on the different principles. He will teach you on the best practices that one should do, or the industrial practices, because he is the one who is manufacturing those circuits and selling it as well. So he gives his perspective on the electric circuits course. And then, of course, you can follow Wolfram System Modeler on LinkedIn, where we share the upcoming events, so you can keep track of that. Leo, before I go to the next slide, like, can you just give a quick uh, overview of your upcoming electric circuit study group? What one should expect?
Yes, so what I'm working there is trying to create the electric circuits course that I wish I would have had when I was when I started studying. So I try to go like little by little, uh, explaining electrical engineering concepts up to the point where I start showing how to create like some of these analog synthesizer blocks. So that's like the end point, getting like a more theoretical point of view on how to be able of designing this kind of circuits.
Right. And then I also know that you are creating your own circuit boards, which the participants can make. Am I right, or am I mistaken?
Yes, hopefully by the time that I finish the course, there will be available somewhere to download or probably on my own store
Right.
some boards that people can manufacture by themselves or just buy from me for a small donation
Right.
to build like these circuits.
Yes. We had a question of on Yap that do we have any references or recommendations on discrete modeling? So uh, we we covered the function create system model, right? So in Wolfram language, we have a function called discrete input output model where you can use like what would be the next value depending on the past time events, right? And those kind of discrete type of modeling you can use with you can do with this function, and the output of this function is a discrete output model, and you can pass it to the create system model function, and it will give you a system modeler object as well. So let's say you have a system, you have a new process for which you know how the system would respond. You would use this discrete input output model to model it, and then you can create a system modeler object by passing it on to create system model function, and then you could get a block, and then you can combine that block with the other elements in system modeler. So that way it is possible, and that is not listed here in my notebook. That's why I just wanted to mention right away.
Right. Also, we have the clock library, right, Ankit, in system
Yes,
modeler.
yes, of course. You are right with that. So there are two ways for discrete modeling. So inside the blocks, we have a discrete package here, which has samplers, first order hold, transfer function blocks, and other things. So that is one way of modeling discrete things. So you can combine your continuous signals along with this discrete models, and you can do the discrete modeling. You can have unit delays, and then you can create those sample points, and then you can work with it. Or
Right.
Vedant, as you rightly mentioned, we have this clocked library where you can use integer signals, perhaps is
A
so you have
sampler, yeah,
examples
you
here.
can,
Yeah, so you have this is the
not the
simple one.
continuous, the hybrid one of the hybrid one, and we can also talk about
Mm,
to have, yeah,
this
that
one.
one.
So here you're combining continuous and discrete systems using samplers.
Right, and this reflects a real scenario, a real world scenario in which you have the continuous system running there as like a DC motor, you see, which has inertia and torque applied, etc. And then you have, let's say, a sensor which takes measurement with a sampling rate, right? And
Yes.
then you design your discrete controller and try to,
Yes.
yeah,
Yes.
achieve your goal with
Yes.
DC
S-
controller.
Yes, so there are three ways. Either you can use discrete input output model in the Wolfram language. You can use the discrete block in the blocks library in Modelica package, or you can use the clocked library and try to see if those features work. And if you want to do something else, uh, if you can send us what is the use case, or you can post it in the community, then we will try to see if we happen to have done something similar, and we can get back, right? And finally, if you have more questions, as I said, please post it on our system modeler community, and me, Leo, Vedat, and we have other developers who will be very happy to answer to your queries. And with that, thank you all. It has been a very long 9 sessions, and I think all the sessions exceeded the time limit. I'm really extremely sorry about that. But the thing was, we thought it is very simple in our mind, and as soon as we started modeling it, we have like, and we started dealing with the details. It just exploded. But I hope during the live modeling process, you saw us doing things live, and that's how real modeling process happens. It's not a smooth journey, but a lot of trials and errors,
Right,
lot of errors, lot
right.
of fixing of errors.
Ups and downs, yeah.
Yeah. Okay, Leo, any final words from your side?
No, just thank you and have fun with System Modeler.